Out. Okay, now it's recording. So thanks a lot for attending this afternoon talk. Today we have the pleasure to have with us Yonit Okbe, that she's going to speak about new direction for light dark matter. So let's go on, please. Yonit, is yours.
Okay. So thanks so much, Luca, and hi everyone. It's nice to meet you, even if it's all unfortunately just virtual. I wish I could. Hopefully, I'll get to meet you one day in person too. So the topic I'm going to talk about is something that I've been very interested in over the last few years, and very active in this field. And I think it's really an active and emerging new field. So hopefully, I get to share some of what I find to be exciting about this field with you, and maybe get you interested in it as well. So I'm going to start by telling you why I think light dark matter is interesting. And then we're going to delve into how we can hope to explore it. And I'm going to show you this from two perspectives, both from the theory side as well as from the experimental side. And I will say I myself am a theorist, but I work on both new theoretical ideas as well as new conceptual ideas for experiments, as I'll be explaining. So let's start at the beginning. As I'm sure you all know, our universe is dark. Nearly 30% of the energy content in our universe is made of dark matter. And though we don't know its exact identity, we do know that there's no suitable candidate for dark matter within the standard model of particle physics. And that means that we have to have at least one new stable, or if not stable, extremely long-lived particle that should exist in our universe today. And the question that we're trying to answer is, what is this particle or particles, and how do they interact with themselves and with ordinary matter? So what do we know about dark matter? Well, we know that it has roughly 5 times the mass density of baryons. So, roughly that means that if the mass of dark matter is of order the mass of the proton, then there's, a dark matter particle in your cup of coffee. We know that it's massive, but we have no idea what its mass actually is. We know that it can't interact too strongly with the known forces, with quantum electrodynamics and quantum chromodynamics, because if it did, we would have already detected it. And we also know that it shouldn't interact too strongly with itself, because these strong self-interactions can distort dynamics in dark matter halos. And it's no secret that the star of the show for the last 40 years or so has been the WIMP, the glorious WIMP, with, of course, appropriately stated caveats about axions. And the idea is actually extremely simple, as I'm sure you're all familiar with, that if we have some particle, some dark matter particle that has 2-to-2 interactions with ordinary matter, with standard model particles, then we can have some relic abundance left over. And so if we just parameterize that annihilation, 2-to-2 annihilation cross-section as some coupling squared over mass squared, then you get that we get the right amount of relic abundance of dark matter in our universe today if there's a particular size for this cross-section, or in other words, there's a particular relationship between the mass and the coupling, which tells you that the mass should be around that coupling times 30 TeV or so. And so it happens to be the case that if this coupling is of order an electroweak coupling of order 10 to the minus 2, then the weak scale emerges. Okay, so this is what we all know as the weakly interacting massive particle, the WIMP miracle. And this WIMP miracle has been guiding, has really been the dominant notion for dark matter for nearly 4 decades. And it's really easy to understand why, right? It's simple, it's predictive, and of course it relates to the hierarchy problem in that it gives us new particles at or above the weak scale. And so as this has been our dominant notion for so many years, it's also been guiding experimental searches. So we search for WIMPs and for dark matter in a variety of different ways. We search via direct production, where we smash standard model particles on each other, hoping to produce dark matter particles that we'll be able to somehow detect. This is, for instance, of course, what we do at the LHC. We search via direct detection, where the idea here is that we take some big pool of standard model particles that are sitting in a lab, typically deep underground, and we hope that dark matter would come and sort of scatter off of this big pool of particles that we know their properties of, and leave some imprint in our detector. So this is, for instance, an image from a Xenon 110 experiment. And we also search via indirect detection, where here we look to the sky, of course, not using our bare eyes, using fancy telescopes, and we hope to see some annihilation or decay products, electrons, positrons, photons, something like that, ordinary particles that are coming out from interactions of dark matter that are occurring around us. And so we've been searching for some time, and unfortunately, we haven't yet found these particles. And this is true on all of these different frontiers. These experiments are getting increasingly sensitive and doing an amazing job at probing the WIMP parameter space, but we haven't yet detected dark matter. And so what I'd like to argue is that the status of dark matter now in 2021 is that really our dominant notion is being challenged. And I think that if a sociologist was looking at the high energy community in general, they'd be able to detect a clear shift in mindset, where sort of historically, we have these big puzzles of physics beyond the standard model. And the thought would be that, it would be great if a solution to these big puzzles would give us an option for a dark matter candidate. So big puzzles, of course, call for big ideas, supersymmetry, extra dimensions, etc. And whereas sort of in recent times, there's been a shift to a more, I think, simple and concrete mindset where we know that dark matter exists. And so we have to explain it, period. And it's possible that it's coupled to these other issues, but maybe it's decoupled from those other puzzles. So it's really important that we think outside of the WIMP box. And I'd argue that this is something that we should be doing both theoretically and experimentally. Because if you think about it, the mass range that we think of for the WIMP really spans just a small fraction out of a vast parameter space in which dark matter can reside. Dark matter could be many, 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 many orders of magnitude above, or many, 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 many orders of magnitude above, below the WIMP mass range. Okay, there's some 80 orders of magnitude roughly where it can reside. And so what I'd like to focus on in this talk is on the possibility of going lighter, in particular between 3 to 6 to even 12 orders of magnitude below the mass of the proton, below a GeV. And this is a field that's seen really a lot of activity in recent years, both from the theory side and the experimental side. And of course, as we make progress in one, it really sort of informs the other and pushes the field forward. So I'd like to give you a little bit of a taste of this activity. So we're going to start with the theory side. So new theory ideas for light dark matter are actually very abundant. Here is a very short laundry list, by no means a comprehensive list. And what I'd like to do is just sort of walk you through a few of these to give you a sense of how broad and how generic these ideas are. So how can we get light dark matter beneath a GeV from the theory perspective? So let's start with example number 1. It's just weakly coupled 2 to 2. Okay, so let's still look at the exact same process that we looked at for the WIMP. Dark matter annihilating into 2 things. We still have the exact same cross-section with the exact same relationship between mass and coupling, except now instead of taking this coupling to be of order an electroweak coupling, let's just take the coupling to be much smaller. You naturally get dark matter that's substantially lighter than the weak scale. So that was pretty easy. Example number 2 are what we call forbidden channels. So here we still think of a 2 to 2 annihilation process where 2 dark matter particles annihilate into 2 ions, 2 things, but let's look at it at a kinematic regime where the sum of the incoming masses is smaller than the sum of the outgoing masses. Now this, of course, at 0 temperature, this process would be forbidden. It would be kinematically disallowed, but fortunately the early universe is a thermal environment. And so in the early universe, this process can proceed by living off of the Boltzmann tail of the particle distributions. And so if you work out the relationship in this case between mass and coupling in order to get the right amount of dark matter, you start off with something that looks very similar to the case of the WIMP, except now there's an additional exponential factor, okay, which cares about these mass differences, which is exactly coming from this Boltzmann suppression of the distribution. And so in this case, you can naturally get dark matter that is exponentially lighter than the WIMP. Example number 3, what if what's important isn't so much how dark matter interacts with other stuff, but how it interacts with itself? So in this case, the first process where dark matter self-interacts with itself that does change the number density of dark matter in the early universe are 3 to 2 self-annihilations where 3 dark matter particles collide and shoot out 2 dark matter particles. So let's parameterize this 3 to 2 cross-section as some coupling cubed over mass to the 5th. In terms of dimensions, this is correct. What you'd find in this case is that in order to get the right amount of dark matter that we observe in the universe, there's a very different relationship between that coupling and the mass. You find now that the mass goes like the coupling times 100 MeV or so. And so now it happens to be the case that if this coupling is of order a strong coupling, an order 1 coupling, the strong scale emerges. And so instead of a weakly interacting massive particle, we call this a strongly interacting massive particle. Or instead of a WIMP, it's now a SIMP. Now, of course, if this was the only process that existed, then these 3 to 2 annihilations pump heat into the system, right? Because if 3 guys come in, 2 shoot out, they're each more energetic than the ones that started off. And so there has to be some way to shed that heat. There has to be some way to dump that entropy. And the way that you can do this is by having some thermalization process, such as elastic scattering, that's happening that's allowing you to thermalize with the light standard model species. And this is a process that needs to be active while the freeze out of the 3 to 2 process is occurring. So in the SIMP mechanism, what we have over here are really these 2 knobs of the 3 to 2 self interactions, as well as a weak coupling that is controlling, that is allowing thermalization. So As I said, in the SIM process, really, we have these two knobs. And what's important is that the 3-to-2 annihilation determines the relic density of dark matter. And it's the process that decouples first and the thermalization continues throughout. But you can ask yourself, what would happen if the order was reversed between these two processes? Well, in this case, you'd find a very different dark matter candidate. You'd find that, surprisingly, the relic abundance of dark matter is exponentially sensitive to the size of that elastic scattering cross-section, okay? So in this case, it's this elastic scattering that's determining the relic density. And so this is called an elastically decoupling relic, or in short, it's called an elder. And in fact, it turns out that if you just look at if you consider the relative size between these two knobs, how strongly dark matter couples to standard model particles versus how strongly the 3-to-2 interactions are occurring, what you find is that actually you sort of flow from a regime where you're very WIMP-like to a regime where you're SIMP-like to a regime where you're an elder. And so these different mechanisms for dark matter are really spanning sort of different phases in this parameter space. And what I think is really nice about these, and I've just shown you a few examples for new mechanisms that would give us light dark matter, is that these ideas are actually very generic. And what do I mean by that? Well, just think about our beautiful visible sector. We have a standard model of particle physics that contains a whole zoo of particles, and it has a beautiful structure, symmetry structure, that's governing everything about the interactions, the SU3 cross SU2 cross U1. And you could ask yourself, why couldn't the dark sector similarly have this whole zoo of particles, maybe organized by some new gauge symmetries, by some dark symmetries as well? And so, staying sort of inspired by the visible sector, by the standard model, maybe just like we have QCD and SU3 gauge theory, maybe there's a dark SU3. And it doesn't even have to be so similar to QCD. Maybe it's some general SPNC or SU gauge group or SO gauge group. And maybe just like we have our photon U1 electromagnetism, maybe there's a dark U1 force in the dark sector, which would give us a hidden photon, a dark photon, and perhaps it can kinetically mix with our ordinary photons. This is just to give you sort of an example of strongly coupled gauge theories that could exist in the dark sector. And these theories are really just QCD-like theories, okay? They're theories of chiral symmetry breaking, and in which what I'm going to show you is that actually the pions, the pseudonumber Goldstone bosons of these theories could play the role of dark matter. And what's really beautiful here is that these theories are so rich. It's really a very rich playground for dark matter physics to emerge. There are so many processes, and then they can really easily realize many dark matter mechanisms. So for instance, perhaps to show you one that seems a little exotic from what I've shown you before, let's think about these 3-to-2 annihilations that we need for SIMP dark matter. So again, just think about QCD, okay, before we think about dark matter. QCD actually has 5-point interactions. We have annihilations of 2 kaons going to 3 pions. This is a process that happens through a topological term that exists in the QCD Lagrangian, which is known as the Wess-Omino-Witten term. And in fact, if you took that Wess-Omino-Witten term that exists in the standard model and you calculate the rate, you'd find that the rate for this 3-to-2 process is just right to be a SIMP if the mass was of order a few hundred MeV. And so inspired by this, just think about an SP gauge theory, an SU gauge theory, an SO gauge theory with 2 or 3 more flavors depending on the gauge group. In all of these theories, the Wess-Omino-Witten term exists. There's a topological condition that is met. You can write down the particular form, and you see it involves 5 pions and 4 derivatives with a coupling strength that that cares about the pion decay constant and the number of colors. But in all of these theories, we have these 5-point interactions. And what you find then generically is that you do have SIMP dark matter that naturally occurs in these theories. You have stable dark matter in the form of these dark pions, and their mass is typically pointed to be of order a few hundred MeV. And this is completely non-exotic. This is just something that is generic in these theories. These theories, of course, also have glue balls, and there have also been interesting works about showing how 3-to-2 could also be happening through glue balls, dark glue balls as well. These processes don't just have 3-to-2 interactions, but they can also realize a variety of different 2-to-2 interactions, which can lead to different dark matter mechanisms. So for instance, we could have these forbidden channels, forbidden annihilations, where dark pions, so all particles here, unless they're labeled standard model, are dark particles. We could have 2 dark pions annihilating into 2 heavier rho particles to give us forbidden channels. We could have 2-to-2 annihilations either into the hidden photons or into standard model particles themselves. The The elastic scattering process, which is very important for elder dark matter as well as for SIMPs, is also naturally existent here. And we also have semi-annihilations, which occur over here again through the gauged Wess-Lomino-Witten term. So this just goes to show you that these theories are so rich, they naturally accommodate so many different interactions, and depending on the relative strength of these interactions, these theories naturally give you different types of light sub-GeV dark matter. And not only are these...
So you're assuming that the pions always are stable. It's not like in the standard model. You are not allowing them to decay into two
right.
photons or whatever and have the variances. Why don't you consider the option also of having the variances bound, bound variance at dark matter?
Yeah, it's completely possible. So what I wanted to do here is sort of draw what I find to be the easiest example of how this could work in these theories. It's by no means the only way. And I think we're also really just at the beginning of starting to understand the full breadth and richness of what dark theories like this could do. In the context of the pions, the story was just so beautiful by using this Wess-Lomino-Witten term, and because of, it's basically you choose a smart U1 that you're gauging out of your flavor symmetry, and then you end up with completely stable particles, and so there's no question mark about whether or not your dark matter is decaying. It's by no means the only way to do it. So it definitely could be very interesting, to consider also, absolutely to consider dark baryons. I think there's been a few works, not necessarily, full. I don't think there's been like a systematic study for all gauge groups, but there's definitely, I think there's definitely a lot of interesting work to be done in that context, whether it's for SIMPs or for any of these other processes in these very rich dark sectors. So what's nice is that these ideas are not only, as I hope I've convinced you, very generic in sort of strongly coupled gauge theories, but they're also very predictive. So again, just to give you a sense of this, so let's, for instance, let's look at this case over here. I've chosen, I fixed the gauge group, the dark gauge group, let's say to be an SU2 with 2 flavors. We also have this kinetically mixed U1, fixed the dark matter mass. So just to show you over here, this is the x-axis is a function of the kinetically mixed hidden photon. The y-axis is showing the size of that kinetic mixing, which effectively controls the coupling of this vector to the electromagnetic current. And what you just see over here, all of these different curves are showing you regimes in this parameter space where different types of processes are important. So can you guys see can you see my mouse when I'm moving it?
Yes.
Okay. Great. So so you see over here, this is the line where 2-to-2 annihilation, the ordinary sort of WIMP-like, but taking it to be very weakly coupled, would be controlling the relic abundance. This is a regime where the SIMP process is what's important. Here's the line for thermalization. This is where elder dark matter exists. Over here, we'd have dark matter that isn't thermalized with the standard model, and this is a region where semi-annihilations contribute. So this shows you that in this parameter space, different regimes simply cover different types of processes with relative importance. And on this type of parameter space, we have, of course, many existing constraints. This plot is a few years, I pulled this from a paper that we wrote a few years ago, so there might be some small updates to the constraints. You see over here in gray, shaded gray, are all the existing constraints on this parameter space. And all of these different solid curves are showing you projected reach of a variety of high energy, low energy machines, fixed targets, beam dumps, et cetera, to probe this parameter space. But I think maybe what's even more exciting than sort of talking about how we could probe, and it's of course wonderful how we could probe this kinetically mixed hidden photon, what I find to be really exciting is that we could actually perform even dark spectroscopy of the dark sector itself. So what do I mean by that? So let's again think about just ordinary QCD. Okay, so how do we know the beautiful intricate structure of all the resonances in QCD? Well, what we do is we smash electron positrons on each other, right? And it goes to all sorts of stuff, to all these resonances. And by scanning that center of mass energy, we're effectively scanning and hitting all of these resonances. So that's how we trace the QCD resonance structure. But you could ask yourself, how could I have done this if I had a fixed energy machine? And the answer is look at monophoton events. Okay, look at the energy of a monophoton coming out, because the energy of that monophoton is in one-to-one correspondence with the energy, the invariant mass of the system that you're not seeing that it's recoiling against. Okay, and so for this exact reason, you could just do this for a dark sector as well. Okay, so if you look at monophoton events, what you just have is that energy of the monophoton is in one-to-one correspondence with the invariant mass of this hidden, of potentially a hidden particle that it's recoiling against. And so just to give you a sense of this, here's, for instance, just a projection for, something that could be done at Belle 2, showing you over here how if you had, this is for a SIMP-like dark sector, how you could hope to see this, sort of tower of dark resonances, dark row resonances in this case, just by looking at monophoton events. So this is what I mean by performing dark spectroscopy at low energy machines. Okay, so having told you a little bit about sort of new developments and ways that we can get light dark matter and what we can hope to achieve with light dark matter from the theory perspective, I want to tell you now a little bit about what we can hope to do from the experimental side. So we have many existing experiments, of course, for dark matter, and they sort of all follow the same general blueprint. Okay, so the idea is that we take some target, some stuff that we know its, we know its properties, we know how it behaves roughly, and we put it in a lab deep underground. And the hope is the dark matter is going to come in, it's going to hit that target that's sitting in the lab, it's going to have, the system's going to react in some way, and we hope to measure that reaction. Okay, so dark matter comes in, it's hitting the target, maybe it's shooting out electrons or phonons, or it's moving it to an excited state. Something's going to happen, and we hope to measure that stuff that happened. Okay. And so here's a plot that I'm sure you've seen the likes of many times. It's the type of plot that we get to see from direct detection experiments that show us, because we haven't yet detected dark matter, the size of the constraint that they can place on the cross section between dark matter and the nucleon as a function of dark matter mass. And this is, by the way, taken from a very cool website that SuperCDMS runs, where you can just select which existing constraints you want to put on a plot, and it sort of compiles everything together. So if you ever want to play around with that, it's pretty cute. But what you see common to all of these different curves, which are showing you results from all of these different experiments, is that they're all sort of going down here, and then they're all shooting up. Okay, so what's going on in this region? Why are all these experiments losing sensitivity when the dark matter mass drops beneath a few GeV or so? And the reason is that what current experiments are typically doing is looking for nuclear recoil signals. Now, the energy that's deposited in a nuclear recoil goes like the momentum transfer squared over twice the target mass. Momentum transfer is typically the mass of the dark matter times its velocity. Velocity in natural units, 10 to the minus 3, the speed of light. And of course, if we want to be able to detect these nuclear recoils, then they better be above thresholds, which are typically of order a keV of energy. Okay, but you can really understand everything that's going on just in terms of thinking of billiard balls. Okay, so if I want to detect a heavy WIMP, then makes total sense. Okay, if I have a big dark matter, heavy dark matter particle that's coming in, no problem for it to kick that big heavy nuclei and give it a big enough punch such that I can measure that reaction, because it is going to manage to give it that kick. But if we want to be sensitive to light dark matter, then the kinematics is more like a tiny little ping pong ball that's trying to give a big kick to a big bowling ball. It's just not going to work, right? That light dark matter can't give a big enough punch to kick that heavy nuclei. And so that's why we lose sensitivity when we're looking for nuclear recoils for GeV masses. And so if you want to be sensitive to light dark matter, then it's actually much smarter to scatter off of something lighter, such as electrons, where the kinematics is more well matched, and there's no problem for that tiny ball to come and give a kick to the other tiny ball. Okay, so that's sort of the basic, the fundamental thing that's sitting at the sort of foundation of a lot of most of the new ideas that have been put forward, sort of this new understanding of new avenues to search for light dark matter via scattering off of electrons. And so to understand these different ideas, what I want to do is sort of provide you with an energy guideline to help guide the way that we think of this. So if we're trying to detect dark matter that's scattering with our electrons, then the maximum amount of energy the dark matter could possibly deposit is its entire kinetic energy, right? That's all that it has to give in a scattering event. And so kinetic energy, roughly mass times velocity squared, which means a velocity, again, 10 to the minus 3. So that means that the maximum energy that a particle could possibly give is 10 to the minus 6 times its mass, okay, in a scattering event. And so that means that if we want to be sensitive to GeV scale dark matter, then we need systems that are sensitive indeed to keV energy deposits. But if we want to go 3 orders of magnitude lighter down to an MeV, then we need systems that are sensitive to much smaller energy deposits, to EV energy scales. And if we want to be really greedy and go all the way down to a keV, down to the warm dark matter limit, then we need systems that are sensitive to really tiny energy deposits of order milli electron volt, an MeV. Okay? And so I think we can throw all of the new proposals that exist in the literature, really just looking at the sort of organizing them based on what size of energy deposit can the system be sensitive to. Okay, and there are many new proposals that exist in the literature. Some involve interactions with electrons, some actually also involve interactions with nuclei. There's really been an explosion of ideas and interest in recent times. And what I'd like to do is, again, just sort of walk you through a few of these ideas to give you a little bit of a sense of the different target materials that people are using, the different processes, as well as the different detection philosophies or methods to sort of open your minds towards this direction of thinking. So here's example number one, and these are also the first ideas that were put out, I guess, nearly 8 years ago by now by theorists. And so maybe the idea is that maybe dark matter could come and ionize an atom, or maybe it could come and promote an electron in a semiconductor from the valence band to the conduction band. Okay, so if we wanted to, for instance, ionize a xenon atom, then the ionization energy is ballpark of 10 eV. If we wanted to promote an electron from the valence band to the conduction band in a typical semiconductor like germanium or silicon, and we recently shown that even diamond and silicon carbide are excellent semiconductors for this purpose, the band gaps are of order in EV of energy. And so based on that energy guideline, you already know that what this means is you could be sensitive to dark matter scatterings of ballpark MeV masses. And even though these ideas were put forward and are continuing to be put forward by theorists, these ideas are being experimentally realized. So in the context of atomic ionization, the xenon collaboration and all of its different sizes as it's been going up in size has placed constraints using this method. And leading the charge for the semiconductor story using silicon, Super CDMS and Sensei have already very impressive results, and the Sensei people have even recently, just a few months ago, won the New Horizons Prize exactly for this groundbreaking idea and work. So these ideas are really moving forward into experimental realization. Now, of course, you can ask yourself, okay, so these ideas can be sensitive to MeV dark matter, but what happens if I want to go lighter? That's something that I fundamentally can't do based on this energy gap in these systems through electron excitations. So what happens if we want to go to smaller masses? So in this case, enter idea number 2, which are superconductors. So I'm sure, like myself, you're not condensed matter theorists. So in superconductors, the ground state of the system, it's no longer free particles, but rather it's energetically favorable for the electrons to follow the buddy system. And so they pair up in pairs that are called Cooper pairs. And the binding energy of these pairs, which is the same thing as saying the gap of the system, is of order milli-electron volts. So you can already see why these systems have the potential to be sensitive to keV masses of dark matter. So the idea would be that dark matter comes in, it scatters with these Cooper pairs, it deposits enough energy to break the Cooper pairs apart, and that's something that we can somehow detect. And when we first put out this idea to use superconductors as keV scale dark matter mass detectors around 5 years ago, we were using a philosophy that's very similar to what Super CDMS does, which is called excitation concentration. But what I want to tell you about is actually an idea that we put out just around a year ago, where we use the same little device as both the sensor and the target for dark matter scattering. So what we use is a device that's called a superconducting nanowire single photon detector, or in short, it's called an SNSPD. These are devices that are extremely well studied. They are broadly used in quantum information science. So they've been really, it's a very mature technology. And the idea would be that dark matter could come in, interact with an electron, ram an electron inside these nanowires. What that does, deposits its energy. Now that creates a hotspot. The electrons sort of depart from equilibrium and start to diffuse away. That's going to create this hotspot across the nanowire, which creates a resistive region. And that gets read out as a voltage pulse eventually in this circuit. Okay, so dark matter basically comes in, deposits enough energy, creates this hotspot, and then there's a huge change in the resistance. And what we effectively propose is really just to use this extremely mature technology that's been developed for quantum information science for the first time towards dark matter detection. Okay, so here the idea is that we use the same little nanowire simultaneously as the target with which dark matter is interacting, but also as that sensitive sensor that can detect that these interactions had occurred. And of course, eventually, in order to build up in mass, what you'd have to do is multiplex this. And we actually have an existing prototype device from which we have already taken data and are continuing to take data that really serves as a proof of concept that this idea can indeed detect light dark matter. And I'll show you some results from that in a little bit. So I've told you an idea for using superconductors, but what if we want to get directional information? So, you know, in the original idea that we used, that we proposed for superconductors, and also in what is typically used right now, let's say in super CDMS for semiconductors, what's happening is that what's being detected are actually not the primary particle with which dark matter is interacting, but rather secondary particles that are happening from sort of ricocheting around. And of course, if what you're detecting are secondary particles, you're losing that directional information. And directional detection has long been recognized as a powerful tool for dark matter detection because it gives you a daily modulation rate of the signal, and that of course separates your signal from background. And so if you could detect that the primary particle with which you interacted, you could hope to retain some directional information. And so this is something that we can actually do with two-dimensional targets. And I'm going to tell you the story of how we do this with graphene, but keep in mind that something very similar could actually be done with these nanowires that I just mentioned to you. So graphene is a material that has it's a two-dimensional material, and it has a vanishing band gap, but I'm actually not going to use any of the beautiful properties of graphene at all. All we're going to use is the fact that in order to eject an electron from that material, you have to overcome the work function, and the work function is of order a few eV. Okay, so if I want to eject something from that material, I have to deposit a few eV, and that means that I could have in principle sensitivity to MeV scale dark matter masses. So the idea is that dark matter would come in, it's going to scatter with the valence electrons, deposit enough energy to eject an electron, and we're going to hope to detect that ejected electron. Okay, so this is an eject and detect philosophy. And the real strength of this proposal comes from the fact that when you study the directional dependence of what's happening to that ejected electron, it turns out that it follows really well, it tracks very well the direction of the incoming dark matter particle. Okay, and so this setup naturally gives you a forward-backward discrimination power, which will help you separate signal from background. So what I mean by that is, you know, imagine a situation, you know, here's my graphene sheet, okay, and at a certain point during the day, the dark matter wind is coming exactly from below, okay, then I have an electron that's ejected over here in the forward direction, and I'm able to detect it. Now fast forward 12 hours later, as Earth is rotated around its axis, now the relative direction between this graphene plane and the wind is exactly reversed. Now that electron is going to be ejected, you know, into the substrate, so either not detected or detected as something different. And so this naturally gives me a directionality where I can build sort of a head-tail discrimination, or sort of a forward-backward asymmetry between these events. And so we can hope to have directional detection in this case.
What is theta ER there?
It's just showing you the angular, it's the angle that determines, you know, it's the angle that you care about, the relative angle between the ejected electron and the incoming dark matter.
And you are looking at night or 12 hours later by...
Yeah, exactly. So what you do is you study, so first you need two pieces here to happen. First, you need there to be a correlation between the direction of the ejected electron and the incoming one. And that you do by studying the just the differential distribution of that angle. And you find that indeed it's forward peaked. And then the second piece is, of course, being able to differentiate between when I'm ejected forward and when I'm ejected backward, which is possible in this setup. And so if you wanted to build up in bulk from a two-dimensional target of graphene, so let's say you wanted 0.5 kilogram of graphene. So I checked, what we'd have to do is basically tile the entire old city of Jerusalem, roughly 1 kilometer squared of area. And assuming that the state of Israel would not allow us to do that in order to run a dark matter detection project, you basically need billions of centimeter squared crystals, okay? And so the way that you'd be able to achieve this is by just using a compact geometry where you get this large mass via multiplexing many different stacks. And so the amount of graphene that we're imagining to run really a full-scale experiment roughly fits into a 10-meter cubed space. And you might think that this is crazy. And when we first thought of this idea, we thought it was crazy. How are we ever going to get this much graphene? Until you find out that there is an experiment that's being proposed that is now sort of in the process of being set up, which will have this amount of graphene. So there's an experiment called Ptolemy, which is a proposed experiment to detect relic neutrinos through their capture on tritium. And it turns out that they intend to have their tritium sitting on roughly 0.5 kilogram of graphene. And what we essentially proposed is just to sort of borrow their untritiated graphene sheets to run as a dark matter experiment. And this idea has now been officially accepted by the, officially adopted and accepted by the Ptolemy collaboration, which, as you see, this is taken from a title of one of our recent papers, is now officially also a directional detector experiment for MeV scale dark matter. And we have a really nice worldwide collaboration. And it's nice even as a theorist to be able to participate, at least in some way, in experimental collaboration. Okay, so I've given you examples of a few different types of materials, which each have their own, their own side of strengths. But of course, what happens in any given material, what you have to do is go ahead and compute the rate to understand what is your projected reach. And this comes, there are a few pieces that come into this. So you care about the target density, you care about that flux of incoming dark matter, you care about target properties. This is a piece that usually has to have some interaction with sort of condensed matter physics as input and understanding. And of course, you care about the interaction cross-section, which is where the particle physics comes in. And you take all of this, and then you can compute what is the expected reach for any of these different materials. And here's a plot that we put together for a community report a few years back. So there's a lot of curves over here. What you're seeing on the y-axis is the size of the some reference cross-section of interactions of dark matter with electrons, in this case for a light mediator. And on the x-axis, you're seeing the dark matter mass. And note that this is an MEV now, not like the WIMP plots that we're used to looking at, which are typically GeV. And so let's start with all of these curves that are sitting up here that all sort of lose sensitivity of order MEV. Those are all these different ideas that have these EV scale band gaps or energy thresholds. And over here in green, what you see is this graphene idea. And you see that it does better than some, worse than others, but sort of in the same ballpark of performance. Its real power is that between all of these EV scale energy threshold experiments, it's the only one that has this directional power. And so if we were to see a signal, that would be so important for really knowing that what we're seeing is a signal and not a background. And down here in this dotted green, what you see is the reach for superconductor detectors. Okay, and you see that it really has an amazing, amazing reach. And to show you that this isn't science fiction, as I said, we have an existing prototype device. So we have a superconducting nanowire that's made out of tungsten silicide. It's just 4.3 nanograms of mass. We know that it has at least a 0.8 EV threshold, possibly a lower energy threshold. And at the time that we put out our PRL last year, we had observed it for roughly 3 hours and seen no dark counts. By now, we actually have 30 times more. We have close to 100 hours of data. So hopefully new bounds will be coming from that. And this is the type of plot that we can then show. So you see that this tiny little device looked at for 3 hours. It places this, this black curve that you're seeing over here compared to existing constraints. Now, of course, not yet managing to outbeat existing constraints, which have substantially more exposure, but you see the real power of this, approach. Over here, see if you take, as you increase in mass and you go to lower thresholds while retaining low dark counts, you see that really we have hopes to probe deep into our uncharted parameter space where these other current technologies are simply not going to be able to access. So if superconductors are so awesome, why don't we just stop there? What's the downside? And there is a downside. So the downside is that metals are shiny. It's a very simple statement, but it has deep meaning. Basically what happens is that in-medium effects are actually very substantial inside metals and inside superconductors. You can kind of think of it as if, it's not exactly, but basically the photon picks up a mass. And so if what's mediating the interaction with, between dark matter and electron is a kinetically mixed hidden photon, then what basically happens is that there's a polarization tensor with all of these in-medium effects that really show up in your scattering cross-section and sort of provide a mass into this system. And basically, you take a hit in your reach. Okay, so what that means is that superconductors don't perform as well when you include in-medium effects. And so in come example number 4 for material, Dirac materials to save the day. You can kind of think of these as 3-dimensional versions of graphene. So they're some type of, they're a 3-dimensional material that have these linear dispersion relations. And they're really complementary to superconductors because in them, the photon remains exactly massless. And so here's an example of what the scattering, the reach for Dirac materials would look like. So again, what you're seeing over here, all of these different colored thin curves are showing you the potential prospects for different types of Dirac materials with different types of gaps and other characteristics that just show you that, compared to existing constraints and also to what you see here in black, which would be the superconductor reach. In this case, these materials can really, really probe interesting regimes of parameter space. Okay, and what's also nice is that these materials, because of the anisotropic structure in their lattice, they actually also have prospects for directional detection. And there have, since we put out this idea a few years back, there have been a couple of papers that have been dedicated to looking and to understanding what type of directional detection capabilities we would have. And again, those capabilities are so important when we talk about running a dark matter experiment. Okay, and I'll also just plug in that we have a paper that's actually going to come out hopefully within a week, Friday or something like that, which actually in which we actually develop a new formalism which shows that dark matter, that if you want to talk about dark matter electron scattering in any material, it's actually completely determined by this polarization tensor, by this dielectric function, which is something that you just go ahead and measure in your material. And so with this understanding, we're also able to really provide us with a good handle in order to continue to identify promising materials for dark matter detection. So if you're interested to learn more about that, this is a paper that's going to be appearing in just a few days on the archive. So, so stay tuned for that. Okay, and before ending, I just want to say that, you know, we've been talking about all these different dark matter detector materials. And I want to point out that anytime somebody tells you about some new idea for a target material, it can actually go even further than just dark matter scattering. Okay, so think about this, this energy guideline we were talking about, where in the dark matter scattering, what you deposit is at most your entire kinetic energy. But if you want to think of instead of a scattering process, an absorption process, then in this case, if dark matter comes in, what's being absorbed is the entire mass energy of the dark matter particle, okay? So that means that if we have systems that are sensitive to KeV energy deposits, then although through scattering they're sensitive to GeV mass scales, through absorption they're sensitive to KeV mass scales. Likewise, EV energy deposits sensitive to EV masses through absorption, and milli-EV to milli-EV masses through absorption, okay? So always keep in mind that you can always do scattering and absorption. And what that means is that when you develop a detector that is sensitive to a certain energy deposit, you get two mass ranges for the price of one, okay? And so again, to give you a sense of what this looks like, here's a plot for the absorption reach of a relic kinetically mixed hidden photon. Okay, so this is the mass of this dark photon from EV down to, over here I have 10 milli-EV. And this is showing you that the size of the kinetic mixing. And what you see in all of these different colored curves are the projected reach for all of these different types of materials that I've been telling you about. Okay, and these shaded regions up here are the existing constraints from terrestrial bounds. And you see this blue shaded region over here. That's the bound that's being placed by that tiny little few nanogram looking at it for SNSPD nanowire looking at it just for 3 hours. And you see that it can already provide the strongest terrestrial constraints to date for sub-EV masses. And that's just thanks to the fact that these superconductors are so powerful. And as long as they keep to low energy thresholds, they can really break new ground. Okay, so what are some takeaways? Hopefully I've convinced you that light dark matter is a very active field of research in the last few years. And this is true both from the theory and the experimental side. And I feel like these two really go together and should continue to go together and sort of push the field forward. And importantly, I think that the ideas are really by no means exhausted. We're really only at the beginning of understanding these systems, understanding which systems are the best, and really figuring out how we can determine which systems will perform best and when. And if there's one thing that my experience in the last few years has taught me is that it's totally okay for an idea to seem crazy and even completely crazy at first, because it just might turn out that your totally crazy idea is completely generic in theory land, even though you had never thought of it when you started thinking about this. Or from the flip side, that, you know, some crazy idea that you have, there's some scientist from a completely different field of research who has a tiny little device sitting in their lab that they've never thought to apply towards dark matter detection. So it's totally fine for ideas to be crazy. And I think really that the best ideas are probably still ahead. And personally, also as a young physicist in this field, I find it very, very inspiring that, you know, if I think of where the field was 10 years ago, we had these incredible ideas for how to search for dark matter if it's WIMPs. And those ideas are going to continue to push forward. And it's amazing that they're pushing forward and they're covering amazing ground. But if dark matter was lighter than a GeV, we did not have good ideas of how to search for it. And just looking at how much activity there's been in the last few years, there's really just this it's been such an impressively active field and so many new ideas. And a lot of these ideas, even though we're theorists that are putting these ideas forward, experimentalists are actually going after these ideas. And it's often actually stuff that's sitting sort of at the interface between particle physics and condensed matter physics and quantum information and precision measurements. So I think that there's really a lot that we can learn as these sub-communities from each other, and really a lot of knowledge that sits at the interface that if we just continue to sort of continue to engage and to interact, I think the interplay between these different subfields of physics can really, really lead to a lot of rich understanding and really push the field forward. And so I'll just finish by saying that if you have any crazy ideas, I'm more than happy to be in touch and hear about them. And I'll thank you so much for your time. Are there any questions?
Yes, this is Álvaro de Rújula.
Nice.
I have a question. I take your word for please have crazy ideas. The question is, does any of your very novel methods work at room temperature?
Excellent question. None of the ones that I discussed here today work very well at room temperature. The reason is that just basically thermal noise would really, thermal noise is just awful. So you want to be working at cryogenic temperatures because you want to be suppressing, really just be suppressing any thermal noise. There's a lot of other noise and backgrounds that, as we push to these low thresholds and these super sensitive devices, we're going to find out it exists, and, we couldn't have predicted them. So we're going to try to predict. And, there's definitely a lot of work to be done in that direction, but sort of the minimal thing that one wants to do is really to be able to suppress thermal noise. Having said that, I don't think that there's necessarily like a no-go theorem for, are there any, could there not be an excellent single excitation, single event detector that works at room temperature? I would guess that there probably could be. There's some things that I'm thinking about these days that I don't know necessarily would be as sensitive to needing to go to as low temperature. So I don't think that's a crazy direction to be thinking about. I just think it's always just important to think about, you want to go to something that's very sensitive, low thresholds. You want something that's sensitive to rare events. That's really important because often when you talk, let's say, if we're talking to people who are developing stuff for like CMB measurements or also in the condensed matter theory, often, it's easy to think of something where if you're shooting like this huge flux, there's a huge flux of photons coming in, I can detect it at certain energies. You really want something that's sensitive to rare events. And you also want something that really has sort of like this low dark count, the low intrinsic sort of clicks or events is happening. And I don't think that there's a no-go theorem about why that couldn't necessarily happen at room temperature. Certainly the devices that people have been thinking about are ones that typically need to be operated at very low cryogenic temperatures, but nothing, lower or more crazy than what a good DIL fridge already does these days, so.
You see, if you worked at room temperature, you could eventually extract the kinetic energy of the dark matter. If you compute how much kinetic energy crosses your body in a day from dark matter, you'll be amazed. If you could take away a little percentage of this, you would solve the energy problem.
Okay, so I leave that for you as
get a lot of more support for your research.
So I actually,
well, that's crazy.
Yeah, so sorry, actually, sorry, I'm Brian Saldívar here. About the question of Álvaro, there is this proposals of Dirac materials building, how to call it, this these computers, quantum computers actually, and they work at room temperature. At least this is the original idea or the main motivation for that. So it is not impossible for these new materials to work at room temperature. So Johnny, can I ask you a question on the talk? So is it clear how to deal with background in all these new materials? So is it clear that the background is under control there?
Absolutely not. Some materials we understand a little bit better what types of backgrounds and others no. I think, I think sort of the way that I think, so let me say it this way. So there are sort of two pieces to this. So one is, of course, if you can develop something that's an excellent idea, that's directional detection, you know, that's like your holy grail. If you can do directional detection, you're golden in a way, right? I mean, it's very, very good because you can separate your signal from, you can't separate signal from background, right? You don't expect your background to be modulating in the same way. But even if you don't, you know, even if you don't have a directional detection, I think sort of there's, you know, going from a conceptual concept of how can I detect dark matter and what's a potential reach in an ideal situation where I have zero background, I have, you know, X, I don't know, kilogram of this material, and I look at it for a year, right? Kilogram year sort of just being sort of a standard exposure that we sort of like to compare apples to apples to. What is the reach? That is something that is such an important first step to be doing. After we find some material that has excellent reach from this perspective, then of course you have to be thinking about what are going to be the backgrounds in this material. And some of them you're going to be able to understand, others we're not going to be able to understand, we're going to need to think better about. And then there might be some that, you know, as we figure that out and we realize, you know, that as we sort of figure it out, until we build a prototype device and we start running it, we're not going to find out that something is, you know, we're going to find out surprises. But, you know, fortunately, none of this is sort of being proposed to sort of operate in vacuum. You know, the field of dark matter detection, just the stuff that's going on these days, all of the knowledge in all of the incredible experiments that are running now, even if they're not running for light dark matter, and certainly the ones that are searching for light dark matter, a lot of the knowledge about how to mitigate these backgrounds and how to, you know, how to do proper shielding, et cetera, et cetera. These are things that then, this is knowledge that can be ported over as we sort of move to push forward, and to push beyond. It's certainly very, very crucial. You know, it's like easy in a sense for me. I'm a theorist, so I start off, you know, my first step of a job is sort of thinking of this wacky idea and going ahead and computing it and seeing, is it going to be exciting? Can it give me any protected, you know, any interesting reach? If it doesn't give me any interesting reach when there are zero backgrounds, when it's just the pure just signal case, then, you know, then there's nothing to move forward. But if you don't start with doing that and finding what's an interesting material to have interesting prospects, there's no point to move into that second stage where you talk about backgrounds. But often that's something that we're going to be finding out as we move forward. But that first step of, you know, sort of bringing the idea to life and checking what would be the potential prospect is super crucial. That's not taking, you know, I have complete faith in my amazing, you know, all the amazing experimentalists, and I collaborate with amazing experimentalists, you know, that's like their hard part of the job, that they have to, you know, that they're working and striving to hope to one day be able to, you know, start thinking of this idea now, so that in another 3 years and another 5 years, there's going to be, you know, there'll be some detector that will actually be taking data based on this idea. And of course, as I said, if we can, the ones that are directional, those are, you know, just have that extra super awesome component, because backgrounds are so much less of an issue.
Yes, so I completely agree about the fact that we theorists should be optimists.
Mm-hmm.
It is just that I just wanted to understand if it was the correct impression I had, that some of these curves were actually the best case scenario.
Yeah, they were best case. Yeah, they were, with the exception, you know, if there's a background that we know how to compute. So for instance, like a neutrino background for like a superconducting reach, when I have 10 millieV up to 10 EV dynamical range of acceptance, then I know to compute a worst case scenario of how much PP solar neutrinos would be contributing, assuming that all of the energy ended up, you know, instead of going into the nuclei, going somehow into the electronic system. And that gives me at most 3 events. So, you know, instead of computing a 95% confidence level for 3 events, you computed for 8 point something. So some of those curves might include a factor like that, but that's, you know, that's a very minimal. Yeah, these are absolutely not, these are sort of the ideal theory curves. And of course, that remains to be seen how, you know, how quiet can you actually, can you construct your detector? But as an example, this tiny little nanowire, we don't really understand, nobody understands why these nanowires are so amazing at keeping dark counts low. You look at it for 100 hours and there are like 3 events, 3 dark counts. It's crazy how quiet they are. So sometimes, you know, technology can also, again, you go ahead and you measure and you see how much, you know, you see how much background you end up having. Sometimes it even surprises you, yeah, in ways that you're not expecting. I'm sure that's usually not the side of the surprise that that one gets, that you get reduced background compared to expectation as opposed to larger.
Thanks a lot.
Sure.
Is there any other question or comment? So it seems not. So let's thank Ionit for a nice talk. Very, very. Here it is. So people are virtually clapping. This is what we have now. So thanks again for the talk. It was very, very nice. And hope to see you soon personally.
Yeah, thank you guys so much. I appreciate it.
Thanks to you. Thanks to you.
Take care. Stay safe and healthy.
You too. Thank you.